Hello students, welcome to our physics class. In the previous class, we have studied about Biot-Savart's law and its applications. That is the derivation of expression for magnetic field at the center of current loop. That is B is equal to mu naught Ni divided by 2R, and derivation of expression for magnetic field at a point on the axis of current loop. That is B is equal to mu naught divided by 4 pi 2 pi Ni r square divided by r square plus x square power 3 by 2. So this is moving charges and magnetism part 5. Okay, well, let's start today's class. Okay, first let us discuss about Ampere's circuit law. Actually, this is an alternative form of Biot-Savart's law. So Ampere's circuit law states that the line integral of magnetic field around any closed circuit, the line integral of magnetic field around any closed circuit, that means integration of B vector dot dl vector is equal to mu naught times the total current passing through that closed circuit. So actually this is a statement of Ampere's circuit law. So what is the statement? The line integral of magnetic field around any closed circuit, that is exactly equal to mu naught times the total current passing through this closed circuit. Mu naught times the total current passing through that closed circuit. Okay. So now let us prove the Ampere's circuit law. So actually here first let us consider a long straight current carrying wire. What is this? A long straight current carrying wire. So this is the magnetic field line around the straight current carrying wire. So the direction of magnetic field that can be determined by using right hand thumb rule. The straight current carrying conductor is held in the right hand, thumb pointing in the direction of current. The fingers encircle the conductor, which gives the direction of magnetic field. Is it not? So if the current flowing vertically upwards, so then what is the direction of magnetic field around the current carrying straight current carrying conductor? That is in anti-clockwise. Suppose if the current flowing vertically downwards, then the direction of magnetic field, that is in clockwise. Okay, but here the current flowing through this wire in vertically upward direction, that is why the direction of magnetic field, that is in anti-clockwise. So this direction can be determined by using right hand thumb rule. So after that, here actually this is called Amperian loop or circular loop. Okay, so this loop is called Amperian loop. Now we can choose a small circular element. Okay, this is a small circular element dl. dl is the length of the small circular element. So what is the direction of dl vector? So actually dl vector is tangential to the circular path. Even the magnetic field is also tangential to the circular path. The direction of magnetic field at each and every point on the loop it is always tangential. Even the direction of dl vector at each and every point on the loop is also tangential to the circular path. Okay, so the line integral of magnetic field, it means integration of b vector dot dl vector. So this is the line integral of magnetic field. Circle on integral means the surface is closed. Surface is closed. So the line integral of magnetic field around any closed circuit. So that is equal to here integration of, so b vector and dl vector. Actually, b vector is tangential to the circular path. Even dl vector is also tangential to the circular path. So what is the meaning of dot product of two vectors? So dot product of two vectors, that is given by the product of magnitude of two vectors. Magnitude of b vector is b, magnitude of dl vector is dl, and cosine of the angle in between that. So here b vector and dl vector is parallel. That means what is the angle? Angle in between them is 0 degree, because the direction of magnetic field at each and every point on the perimeter of a closed curve is tangential. Even dl vector is also tangential to the circular loop. So B is constant. The magnitude of magnetic field at any point on the loop is constant, because the observation points on the loop, those points are equidistant from the wire. So that is why the magnitude of magnetic field at any point on the loop is constant, but the direction is always tangential to the circular path. The direction of magnetic field at each and every point on the loop is tangential. Even dl vector is also tangential. So the angle in between b vector and dl vector is 0. So the magnitude of magnetic field, that is constant, because the observation points on the loop, so those points are equidistant from the wire. So b is constant. So just to take it as outside. So b cos 0 is 1, integration of dl. So b integration of dl is L. So B is magnetic field at a point due to a long straight infinite current carrying wire. So actually the mathematical expression for magnetic field at a point due to long straight infinite current carrying wire is mu naught divided by 4 pi 2 I divided by R. R is the radius of the loop. Okay, so into L is the total length of the loop, that is 2 pi r, that is circumference, right? Total length of the loop is 2 pi r. So here r get cancels, 2 into 2 4, 4 get cancels, even pi cancels. So finally we will get the line integral of magnetic field around any closed loop or circuit as equal to mu naught times the total current passing through that closed loop or closed curve or closed circuit. Okay, so this is the proof for Ampere's circuit law. Line integral of magnetic field around any closed, line integral of magnetic field around any closed circuit is equal to mu naught times the total current passing through that closed circuit. So one more statement is also there, that is also very simple. The magnetic field B vector is directed along the tangent to each and every point on the perimeter L of a closed curve, and its magnitude is constant along the curve. Actually, this is the simplified statement of Ampere's circuit law, right? Direction of magnetic field at each and every point on the perimeter L of a closed curve is tangential. Even dl vector is also tangential. So if the magnetic field B vector is directed along the tangent. The magnetic field B vector is directed along the tangent to every point on the perimeter L, every point on the perimeter L of a closed curve, and its magnitude is constant along the curve. The magnitude of magnetic field is constant along the curve. Direction of magnetic field at every point is always tangential. So this is the simplified form of Ampere's circuit law. So the simplified mathematical expression. So this is the mathematical expression for Ampere's circuit law or Ampere's circuit law. So one more mathematical expression is also there, that is PL is equal to mu naught I. This is the simplified mathematical form of Ampere's circuit law. So what is the simplified form of Ampere's circuit law? The magnetic field B vector is directed along the tangent to every point on the perimeter L, of a closed curve, and its magnitude is constant along the curve. So that is the simplified statement of Ampere's circuit law. So what is the statement of Ampere's circuit law? The line integral of magnetic field around any closed circuit is equal to mu naught times the total current passing through that closed circuit. Or magnetic field B vector is directed along the tangent to every point at the perimeter L of a closed curve, and its magnitude is constant along the curve. Okay, the next topic. So this is very important for 3 mark. This is very important for 3 mark. Derivation of expression for magnetic field due to an infinitely long straight wire carrying current using Ampere's circuit law. Okay, first here let us consider a long straight infinitely. This end goes to infinity. So this end is also goes to infinity. Long straight infinite current carrying wire, and then consider Amperian loop. The direction of magnetic field in Amperian loop, so that can be calculated, can be determined by using right hand thumb rule. The straight current carrying conductor is held in the right hand, thumb pointing in the direction of current, fingers encircle the conductor, which gives the direction of magnetic field. So here current flowing vertically upward direction, so the direction of magnetic field around the straight current carrying wire here, that is anti-clockwise. So the direction of magnetic field at each and every point on the perimeter L of a closed curve is always tangential, right? So again here let us consider a small circular element, that is dl. Dl is the length of small circular element. Okay, so the line integral of magnetic field, the line integral of magnetic field around any closed circuit. So integration of B vector dot dl vector, so that is equal to integration of, so dot product of two vectors, that is given by the product of magnitude of two vectors and the cosine of the angle in between them. So here B vector is tangential to the circular path, even dl vector is also tangential to the circular path. What is the angle in between them? So that is 0, right? So cos 0 is 1, and the magnitude of magnetic field is constant along the curve. So these constant taken as outside. B integration of dl cos 0 is 1. So B integration of dl is L. So D, so L value is length of the loop is 2 pi r, or is the radius. Actually here or is the radius, or is the radius of the loop. So now by using Ampere's circuit law, Ampere's circuit law, that is integration of B vector dot dl vector is equal to mu naught I. So here integration of B vector dot dl vector, that is B into 2 pi r. So call this as equation number 1 and call this as equation number 2. So now comparing the two equations 1 and 2. So from equations 1 and 2, so we can conclude that, so here LHS sides are same. So equating the RHS sides, is B into 2 pi r is equal to mu naught I. So B is equal to mu naught I divided by 2 pi r. This can also be written in the form of B is equal to mu naught divided by 4 pi into 2I divided by r. Because mu naught divided by 4 pi is 10 power minus 7. You have just multiply and divided by 2. So then we will get this equation. So this is actually the expression for magnetic field at a point. Magnetic field at a point due to magnetic field at a point due to a long straight infinite current carrying wire or current carrying conductor. So this is actually P is the observation point, so lies on the loop that is located at a distance smaller from the wire. So the magnetic field at point P is mu naught divided by 4 pi 2I divided by r. So this is the mathematical expression for magnetic field at a point due to long straight infinite current carrying conductor, current carrying wire. This mathematical expression is very important. So this is the expression for magnetic field at a point due to long straight infinitely long straight wire carrying current. Okay, now let us discuss about the applications of Ampere's circuital law. So this is actually the first application of Ampere's circuital law. That is derivation of expression for magnetic field inside a current carrying long solenoid. What is the meaning of solenoid? Solenoid means insulated copper wire wound closely in the form of helix. Insulated copper wire wound closely in the form of helix. That is the meaning of a solenoid. What is the meaning of solenoid? Insulated. Solenoid is insulated copper wire wound closely. Insulated copper wire wound closely in the form of helix. In the form of helix. That is the meaning of solenoid. Okay, so actually here this is a current carrying solenoid. What is this? The current carrying solenoid. So these are the magnetic field lines around the current carrying solenoid. Actually, the magnetic field line directions that can be determined by using a right hand thumb rule. So this one is the cross-sectional view. Cross-sectional view of the current carrying solenoid. What is this? The cross-sectional view of current carrying solenoid. Actually here dots represents the turn is directed normally. Turn is directed normally outward, and cross mark indicates turn is directed into the directed normally inwards. Okay, so actually what is this? The cross sectional view. This is solenoid. Okay, so this one is the cross sectional view of the current carrying solenoid. So dot mark shows turn is directed normally outwards. So cross mark shows turn is directed into the plane of the screen here. So dot mark shows turn is directed outwards. Cross mark shows turn is turn TUR and turn is directed into the plane of the screen. So the direction of magnetic field, so that can be determined by using right hand thumb rule. Actually here the fingers encircle. Okay, solenoid is held in the right hand. The fingers encircle, which gives the direction of current in the solenoid, and thumb points in the direction of magnetic field. Okay, now let us consider an Amperian loop, that is A B C D A. That is Amperian loop, rectangular closed path. Okay, let us consider a rectangular closed path, that is A, B, C, D. What is this? This is called Amperian loop. This one is Amperian loop. Okay, so first here, let us consider small n. What is the meaning of small n? Small n means number of turns per unit length. Number of turns per unit length of the solenoid. Small n means number of turns per unit length of the solenoid. Okay. So, what is the total number of turns passing through the Amperian loop? So this is very important here. Small n means number of turns per unit length of the solenoid. So total number of turns passing through the Amperian loop ABCD, that is number of turns per unit length into the length of the loop. Okay, so M into L gives total number of turns passing through the loop. Okay, so here first we have to calculate the line integral of magnetic field. The line integral of magnetic field. Line integral of magnetic field. Integration of B vector dot dl vector. Actually, this is here splits into four parts. Integration of A to B, B vector dot dl vector plus integration of B to C, B vector dot dl vector plus integration of C to D, so B vector dot dl vector plus integration of D to A, so B vector dot dl vector. So AB, so let us consider a small element on AB. So that is dl. dl is the length of the small element. So dl vector, that is from left to right. Even magnetic field B vector is also from left to right. dl vector is parallel to B vector. So what is the angle in between them? That is 0. Dot product of two vectors, that is given by the product of magnitude of two vectors. So magnitude of B vector is B, magnitude of dl vector is dl, and cosine of the angle between B vector and dl vector. Actually here B vector is parallel to dl vector. So that is why theta is 0. Plus integration of, now we can choose a small element on BC. So having the length dl. So here dl vector is vertically upwards. So dl vector is perpendicular to B vector. So what is the angle in between B vector and dl vector? This is B to C. B dl cos 90. Okay. Plus integration of, so actually here there is no magnetic field. Magnetic field outside the current carrying solenoid is 0. Integration of C to D 0 dot dl vector plus, and the last term D to A. So B dl. Now we can choose the small element on dA. So here dl vector is vertically downwards. So this is the direction of magnetic field, that is from left to right. So again dl vector is perpendicular to B vector. So the angle in between B vector and dl vector is 90. So this term goes to 0. Right? Because cos 90 is 0. So this term goes to 0. So this term is also goes 0 into anything is 0. So this term also goes to 0. Again, the second term also goes to 0 because cos 90 is 0. So cos 0 is 1. Finally, we will get, so integration of b dl cos 0. Cos 0 is 1. So the line integral of magnetic field d vector dot dl vector, that is integration of b dl. So integration of b vector dot dl vector, that is equal to, so here b is constant, that is just take it as outside, b integration of dl. So b integration of dl is l. L is the length of the side AB, right? AB length is small l. Okay. Now, according to Ampere's circuit law, according to Ampere's circuit law, the line integral of magnetic field around any closed circuit, that is equal to mu naught times total current passing, total current passing through the loop. Okay, so total current passing through the loop. So integration of b vector dot dl vector, that is equal to mu naught into, okay, total current passing through the loop is number of turns passing through the loop into current in each turn. Okay, so number of turns passing through the loop is NL, right, into current in each turn is I. So this is NLI is the total current passing through the loop. So integration of d vector dot dl vector is BL. So now call this as equation number 1. Call this as equation number 2. So now comparing the two equations 1 and 2. So then we get BL is equal to, this is from equations 1 and 2. Okay, BL is equal to, comparing equations 1 and 2, LHS sides are same, equating the RHS sides, BL, that is equal to mu naught N L I. So L get cancels. So finally, we will get B is equal to mu naught N I. What is this? Magnetic field inside the current carrying solenoid. This is mathematical expression for magnetic field inside a current carrying solenoid. And this is a very important derivation for 5 mark. This is the mathematical expression for magnetic field inside the current carrying solenoid. So what is the meaning of solenoid? Insulated copper wire is wound closely, insulated copper wire wound closely in the form of helix. Magnetic field inside the current carrying solenoid is mu naught Ni. Actually, at edges, the magnetic field is mu naught Ni divided by 2. Okay, so at the edges, the magnetic field is mu naught Ni divided by 2. So at the center, inside, that is mu naught Ni. So this is very important for CET. Okay, look at this animation. So these are the magnetic field lines. So this is a current carrying solenoid. So this is the direction of current. Actually here current starts from positive terminal, right? So these are the magnetic field lines. So the direction of magnetic field, so that can be determined by using right hand thumb rule. So current carrying solenoid is held in the right hand, thumb pointing in the direction of magnetic field, fingers encircle, which gives the direction of current flowing through the solenoid. Actually here, one phase of the current carrying solenoid, that is acts as south pole, and another phase of the current carrying solenoid act as north pole. So this is the magnetic needle. What is this? North pole. This one is north pole. This one is south pole. So south pole is always attracted towards north pole, right? So actually this phase is just behaves like north pole. So this phase is just behaves like south pole, because here north pole is attracted, right? So the direction of magnetic field inside the current carrying solenoid, that can be determined by using right hand thumb rule. Okay. So current carrying solenoid is held in the right hand, thumb pointing in the direction of magnetic field. The fingers encircle the current carrying solenoid, which gives the direction of current flowing in the solenoid. So the next topic is toroidal solenoid. Okay, so this is the toroidal solenoid. So current carrying solenoid, actually that is bent in the form of a ring. Current carrying solenoid, that is solenoid is bent in the form of a ring, that is called a toroidal solenoid, or simply called toroid. So what is this? A toroidal solenoid. So even the direction of magnetic field inside toroidal solenoid, that can also be determined by using right hand thumb rule. Okay, so here held this toroid in right hand, so thumb pointing in the direction of magnetic field, the fingers encircle the toroid, so which gives the direction of current flowing through the turns in toroid. Okay, so held this toroid in right hand, thumb pointing in the direction of magnetic field, the fingers encircle the toroid, which gives the direction of current flowing through turns of toroid. So what is the meaning of toroid? A solenoid is bent in the form of a ring. Solenoid is bent in the form of a ring. It's called toroidal solenoid, or simply called toroid. What is the meaning of toroid? A solenoid is bent in the form of a ring. Okay, the next topic, derivation of expression for magnetic field inside a current carrying toroidal solenoid or toroid. Toroid means a solenoid is bent in the form of a ring. So this is actually the cross-sectional view of a current carrying toroid. So dot mark shows turn is directed normally outward, and cross mark shows turn is directed normally inwards. Okay, dot mark shows turn directed outwards, cross mark shows turn directed inwards. Okay, so held this toroid in right hand, actually thumb pointing in the direction of magnetic field inside the toroid, fingers encircle, which gives the direction of current flowing through toroid. Okay, so here first let us consider 3 Amperian loops. Okay, so this is Amperian loop 1 and having the radius is R1. So this is Amperian loop 2. Okay, and this one having radius is R. And this is Amperian loop 3. And this one having radius is R3. Okay. Actually, here we have to calculate what amount of magnetic field produces inside a current carrying toroidal solenoid. Okay, the first case, first here let us consider n be the number of turns per unit length of toroid. Okay, so total number of turns passing through loop 2 is n into the total length of loop 2, that is having radius is smaller, so that is why n into 2 pi r. 2 pi r is the length of loop 2 into number of turns per unit length of toroid. This one gives the total number of turns passing through the loop 2. Okay, so first let us consider per points in open space of interior of toroid. Okay, so these are the points in open space of interior of toroid. Okay, so that can be calculated by using Ampere's simplified form of Ampere's circuital law. That means the magnetic field B vector is directed along the tangent to each and every point on the parameter L of a closed curve, and its magnitude is constant along the curve. So the simplified mathematical expression BL is equal to mu naught I. So here B1, L1, this is according to Ampere's circuital law. According to Ampere's circuit law, so B1, L1 is equal to mu naught I. B1 is magnetic field in open space of interior of toroid. So L1 is the length of loop 1, that is 2 pi or 1 mu naught. So I is total current passing through loop 1. So what is the total current passing through loop 1? Actually here no turn passing through loop 1. Okay, no turn that is passing through loop 1 means the total current passing through loop 1 is 0. Okay, 0 into anything is 0, 0 divided by anything is 0. So the magnetic field, open space of interior of toroid, that is exactly equal to 0. Okay, and the second case. So for points inside the toroid. For points inside the toroid. So again, according to Ampere's circuit law, so the magnetic field D vector is directed along the tangent to every point on the perimeter L of a closed curve, and its magnitude is constant along the curve. It means B L is equal to mu naught I. So B is magnetic field inside the toroid. So L is the length of loop 2. Length of loop 2, that is 2 pi. So radius of loop 2 is R. 2 pi R is equal to mu naught times I means the total current. Okay. So I means the total current passing through. Here mu naught into total current passing through loop 2. So number of turns passing through loop 2, that is n into 2 pi r, right? N into 2 pi r. This is number of turns passing through loop 2 into current in each turn, that is I. So n 2 pi r into I. So this is the total current passing through loop 2. So 2 pi r cancels here. So B is equal to mu naught n I, right? So this is the magnetic field inside the current carrying toroid. Okay. So magnetic field in the open space of interior of toroid is 0, but magnetic field inside the current carrying toroid, that is not equal to 0, that is mu naught Ni. Actually, this is same as that of the magnetic field inside the current carrying solenoid. Is it not? The magnetic field inside the current carrying solenoid is also mu naught Ni. So even the magnetic field inside the current carrying toroid is also mu naught Ni. And the last case, for points in open space of, so these are the points in open space of exterior of toroid. Okay, points in open space of exterior of toroid. So again, according to Ampere's circuit law, so B3L3 is equal to mu naught times the total current passing through loop 3. Okay, so B3L3 is total length of loop 3, that is 2 pi or 3, that is equal to mu naught. So here total current passing through loop 3 is how much? Total current passing through loop 3, actually that is equal to 0. Why? Because the current coming out of the plane of screen is cancelled by current going into the plane of the screen here, right? So current coming out of the plane of screen is cancelled by the current going into the plane of the screen. Okay, here total current passing through loop 3 is 0. 0 and anything is 0. 0 divided by anything is 0. So magnetic field in open space of exterior of toroid. Exterior to the toroid is equal to 0. So magnetic field in open space of interior to the toroid is 0. Magnetic field in open space of exterior to the toroid. Magnetic field in open space of interior to the toroid. Magnetic field in the open space of exterior to the toroid is 0. But magnetic field inside the toroid, that is not equal to 0, that is B is equal to mu naught Ni, and this is exactly equal to magnetic field inside the current carrying solenoid. Okay, thank you.